method called as boiling of water to remove the bacteria. So let us come to the different methods in the next part. So normally in disinfection we are going to see the chlorine is found to be an ideal type of disinfectant for the disinfection process. So when we know what is the meaning of disinfection and what are the disinfectants, the next process is what are the minor methods of disinfection. So here we are going to see different minor methods, that is the boiling of water, then the second one, that is the treatment with excess lime, third is the treatment with ozone, treatment with iodine and bromine, treatment with ultraviolet rays, treatment with potassium permanganate, and the last one we are going to see it as the treatment with sulfur. So here we are not going to study all the methods, so only few methods are there, so which we are going to study. So coming for the first part, that is boiling of water. So here this bacteria whichever is present in water can be destroyed by boiling of water for a long time. So what is the boiling point of water that we are going to see? It is 100 degrees centigrade. So when the water starts boiling at 100 degrees centigrade, we see that whatever the bacteria we are going to see in the water present, they are going to be killed, and that is why we say that it is purified. So it is an effective method of disinfection, but is not practically possible to boil huge amount of public water supplies. So whenever we are going to go for this particular method, we are going to see that the boiling of water treatment is only possible for household purposes. Means individually you can go for boiling the water. So when it comes to the public service, we cannot go for the large quantity of water to be boiled and then to be supplied. So this is one of the disadvantage of this particular method. So boiling only kills existing germs but cannot take care of future possible contaminants. So here we are going to see that this particular boiling is going to kill only existing germs. So whatever the germs that are present in the water during the process is only be killed, but it is not going to take care of possible contamination whenever it is going to be made available for the public during this particular process. So this method is not used for public waters, but during epidemics, public should be advised to drink boiled water. So normally whenever the epidemics break down, what we do, we are going to suggest the people or the public to go for drinking the boiling water. So this is, I think, almost all the houses, whenever the epidemics break or during if you are not feeling well, the doctors suggest to drink the boiled water. So in order to kill the existing germs. So the next one is the treatment with excess lime. Lime is generally used for water softening. So in case of softening chapter, we have seen that lime was used for the purpose of softening. So here this particular treatment with lime can be used as a disinfection also. So but excess lime is added to water, it can also kill the bacteria. So whenever you are adding the lime in excess quantity, so it will act as a disinfectant and will kill the bacteria. Addition of 14 to 43 ppm of excess lime can remove bacteria up to 99.3% to 100% from highly polluted waters. So whenever during rainy season, if the water comes, normally in rainy season what we see, the water will be turbid in nature. So at that time, whenever you are going to add, say for a 14 to 43 ppm of excess lime, whichever is going to kill about 100% of this infectious bacteria. So by this we can avoid the pollution of water. Excess lime in water makes water excessively alkaline and kills the bacteria. So by adding the excess lime, what we are going to see, the water pH is going to be increased. that is alkalinity of the water is going to be increased, which is going to cause the filling up of the bacteria. Addition of lime raises the pH of water to about 9.5, that is it is made base in nature or basic in nature. This method is practical for disinfection but needs removal of excess lime from water before it can be supplied to the public. One of the disadvantage of this particular treatment is whenever you are going to add the lime in excess, if the lime is added to the required quantity, it only softens the water. But whenever it is going to add excess of 14 to 43 ppm of lime is going to be added in excess, then we say that it is going to kill the germs in 100%. So when you are adding this excess lime, then what happens is after the process, whatever the lime is there which is going to be excess, it has to be removed whenever before going for the supply to the public. This particular lime treatment needs recarbonation to remove excess lime. It cannot cater future contamination of water. This was used in olden days, but now it is rarely used. So what we are going to say is, to remove the excess lime, recarbonation process has to be done. So this method is not going to be effective. It is not going to go for taking care after contamination of water in the future. So this was normally employed by the olden people who used to add the lime for the water treatment. Next, coming for the next method is treatment with ozone. We are going to see that ozone is a faintly blue gas of pungent odor and is an excellent disinfectant. So normally we see ozone as a cover for the atmosphere, isn't it? So it is going to act as a barrier for the ultraviolet rays that are coming from sun to earth. So this particular ozone can also be used as one of the treatment for purification of the water. Ozone is an unstable form of oxygen. So this ozone, what is the molecular form? This one indication of ozone, that is O3. It is represented by O3. So this is this ozone. We are going to see that it is an unstable form of oxygen with 3 oxygen atoms. So here in ozone we are going to see the atoms of oxygen as 3. It can be produced by passing a high tension electric current through a stream of air in a closed chamber. So normally ozone is available in nature, but when we want to go for artificial creation or artificial manufacturing of ozone, we can see that it can be produced by passing a high tension electric current through a stream of air in a closed chamber. So when we do this process, we are going to get 2 molecules of ozone. Then the ozone molecule thus formed is highly unstable and breaks down into normal oxygen and releases oxygen, that is nascent oxygen. So we are going to see that whenever the reaction process takes place, what happens? The ozone, in presence of electric current through a stream of air, it will break down. Since it is very unstable, it is going to break down into oxygen and nascent oxygen. So this treatment, this nascent oxygen so produced is a powerful oxidizing agent and removes organic matter and also bacteria from water. So whatever the free oxygen that is available or the nascent oxygen which is available is going to form a powerful oxidizing agent. By this process, we can remove the organic matter and also the bacteria which are present in the water. During the treatment, ozone gas is manufactured and bubbled through water containing in a sterilizing chamber. The ozonized water comes out through the outlet at the top. So this particular treatment explains how this ozone is going to be released. That is, during the treatment, what happens? Ozone gas is manufactured and bubbled through water containing in a sterilizing chamber. So the ozone forms a bubbles in a water and it will get out from the sterilizing chamber. The ozonized water comes out through the outlet at the top. So this particular ozonized water which has been which is going to be purified will come out at the top. So 2 to 3 ppm of ozone is generally consumed. What the statistics says that when we are going to treat the water with ozone, approximately 2 to 3 ppm of ozone is generally consumed so as to obtain a residual ozone of 0.1 ppm after a contact period of 10 minutes. So whenever your water is going to be treated for 2 to 3 ppm of ozone, we see that a residual ozone of 0.1 ppm is left out after a contact period of 10 minutes. When you make the contact between the ozone and the water, we see that approximately, that is 0.1 ppm of ozone, that is residual ozone, will be seen in the water. So next coming for a treatment with iodine and bromine. So the addition of iodine and bromine to water, so actually this particular method is not there. So just I am going to give a brief introduction regarding the other treatments also. Treatment with iodine and bromine, the addition of bacteria. So this treatment pathogenic bacteria. The quantity of this disinfectant used is 8 ppm and a contact period of 5 minutes. So whatever the iodine and bromine we are going to use will be of 8 ppm and the contact period with water we are going to see it as 5 minutes. These are available in the form of pills, means tablet like this thing, pills like material we are going to see, it is available in the form of pills, or what we are going to say a tablet, iodine and bromine, and that we can add it to water. These are used to treat small water supplies for army troops, private plants or swimming pools. So normally in your swimming pools also this iodine and bromine tablet will be dropped so as to make it as a disinfectant water. So treatment with ultraviolet rays. So the ultraviolet rays can also be used for the treatment of water. So what actually happens in this particular process? Ultraviolet rays are found in sunlight. So normally we know that UV rays are found in sunlight, but can also be produced by passing electric current through mercury enclosed in a quartz bulb. So this can be artificially prepared. These UV rays can be artificially prepared by passing electric current through mercury enclosed in a quartz bulb. Mercury vapor lamps enclosed in quartz bulbs can therefore be used as a good source of ultraviolet rays. So this forms a good source of ultraviolet rays. So water to be treated with this method should generally be colorless and turbidity should not exceed 15 mg per liter. So normally whatever the treatment we are doing using the ultraviolet rays, it has some conditions. So what are these conditions? It should be colorless. First of all, that is, it should not be turbid in nature, and if the turbidity is there, the turbidity should not exceed 15 mg per liter. For treatment, water is passed several times around the quartz bulbs emitting such rays. So for this treatment, what we are going to see, the water is going to be passed several times, means many times around the quartz bulbs emitting such rays. So whenever the rays are going to be emitted from the bulb, whenever the water passes around this particular bulb, we see that these rays act as a disinfectant to kill the bacteria. So the depth over the bulb should be less than 10 centimeters as these rays effective for such depth. So we are going to see that the depth of the water over the bulb should be less than 10 centimeters, and as these rays effective for such depth. Disinfection with this method does not impart any additional taste or odor to water as no chemicals are added. So one advantage of this UV method is we are not going to see that there is change in the taste or odor of the water. This method is expensive and needs technical knowledge. So normally it is going to be very costly, and the person who is operating this process should be technically strong. This method is generally used to treat small quantities of water in hospitals, dispensaries or surgical uses, and also in swimming pools, mainly in developed countries. So swimming pool in our country we are not going to use this method. Only in case of developed countries we can use this ultraviolet rays for treating the swimming pools, and commonly we are going to see this method is used in hospitals and small dispensaries for surgical uses. Treatment with potassium. So I think in all houses we are going to see some people will be keeping. I don't know whether you all are keeping in the house, but some people normally they keep potassium permanganate. Normally why we keep it? So to wash the vegetables bought from the market, we use this potassium permanganate. This is one of the disinfectants. So we use this potassium permanganate for cleaning the vegetables also. So this is mainly used in disinfecting well water. So wherever the well water we are going to use, so this potassium permanganate, if we add it to water, it will act as a disinfectant and it is going to kill the bacteria. It helps in oxidizing the taste producing organic matter. So what advantage we have by using this potassium permanganate is it is going to be it is acting as a dissolved in, whenever you are going to add this potassium permanganate, it is going to be dissolved in a bucket of water and it is going to be mixed with well water thoroughly. So it is going to add taste to the organic matter, and also it is going to act as a disinfectant. The addition of this produces pink color. So I think all have seen in your laboratory, when you add potassium permanganate to the water, it is going to give you pink color water. So add until pink color stands. So this is one of the advantage, that whenever we add potassium permanganate to the water, if the pink color rests, means stay for more time, then we can say it is free from the organic matter, or else we are going to see that the presence of organic matter is there in the water and more quantity of potassium permanganate is to be added. The well water should not be used at least for 48 hours after addition. So we see that the well water should not be used after for at least for 2 days or 48 hours after the addition of potassium permanganate. The normal doses vary from 1 to 2 mg per liter with a contact period of 4 to 6 hours. So normally we see that the normal doses which we are going to see is 1 to 2 mg per liter with a contact period of 4 to 6 hours. So treatment with silver. So this is last method I think we can go. That is, metallic silver ions are introduced into water by passing it through a tube containing solid silver electrodes which are connected to a DC supply of 1.5 volts. This explains how the arrangement has to be made for treating the water with silver. The silver ions thus introduced is used for disinfection. So whenever you are going to introduce the electrodes which are made up of solid silver and pass a DC supply of 1.5 volts, the ions, silver ions, are going to be released into the water which are going to act as the disinfectant. The silver dose vary between 0.05 to 0.1 mg per liter for a contact period of 15 minutes to 3 hours. So here we are going to see the contact period is going to become more. That is, it may be from 15 minutes to 3 hours. This is a very expensive process. So normally that is why we are not going to use this method, because it is going to be a very expensive process. So coming for our good old method, that is chlorination. So chlorination is normally till today, from many long years to till today, whatever we are going to see for a public water, the disinfectant is going to be added is the one and only one is the chlorine. So chlorine is used for disinfection in public water supply. So normally we are seeing this in our municipality or corporation water. It is cheap. The main advantage of using this chlorine is, it is first of all, it is a cheap material, reliable, easy to handle and easily measurable. So what we are going to say is, in all respects chlorination is a perfect one, and we can say that since it is cheap, reliable, easy to handle, easy to measure, we can use this method. It not only kills bacteria present in water, but also takes care of future contamination of water. So after adding the chlorine, what we see is, it not only kills the bacteria, it also takes care of future contamination of water. So in future, whatever the contamination during the process of water supply, if the pipeline consists of any bacteria, that disinfection also is going to be done by this chlorination. When used in greater amount, it imparts bitter taste and bad taste to water. So this normally we experience in our houses during rainy season. So whenever there will be heavy rain, what the municipality or the corporation people will do, they are going to add this chlorine in larger quantity, that is greater quantity. At that time, whenever the water is supplied to the public, when we consume it, we can see that there will be some bitter taste or bad odor of chlorine present in the water. So disinfecting action of chlorine. So how actually this chlorine is going to act as a disinfectant whenever it is added to the water. So when chlorine is added to water, it forms a hypochlorous acid or hypochlorite ions. So we can see the reaction, that is Cl2 plus H2O. So that is Cl2 is nothing but chlorine, H2O is nothing but water. When both are going to come in contact, it is going to form hypochlorous acid, that is HOCl plus HCl, that is hypochlorite ions. So next is the hypochlorous acid that is going to be formed is unstable and may break into hydrogen ions and hypochlorite ions. So whatever the hypochlorous acid, whichever is formed, is unstable in nature. So it cannot stay for a long time. So this HOCl is going to be further broken into H plus ion and OCl minus ion. The above reaction is reversible and depends on pH of the water. So whatever the reaction that is going to be taking place in chlorination are reversible reaction. Again, it is going to form HOCl, and HOCl plus HCl is again going to form the chlorine. So this is which depends mainly upon the pH of the water. The dissociation of hypochlorous acid into ions is more effective at high pH values and vice versa. So this dissociation is normally is more effective at high pH values, means at a alkaline condition it is more effective and vice versa. So disinfecting action of chlorine at the pH values greater than 10, only OCl ions are formed. So whenever your pH of the water is greater than 10, then we are going to say that only OCl ions are formed. In pH values less than 7, that is more than 5, HOCl will exist without dissociating into OCl ions. So whenever the pH of the water which is greater than 5 and less than 7, this particular HOCl, hypochlorous acid, it will exist without dissociating into OCl ions. In pH below 5, chlorine does not react and remains as elemental chlorine. So whenever the water pH value is below 5, that is less than 5, we are going to see that chlorine is not going to react and it remains as a elemental chlorine. Out of these forms of free available chlorine, the hypochlorous acid is most destructive, about 80 times more effective than the hypochlorite ions. So we are going to see that this hypochlorous acid is most destructive, that is at about 80 times more effective than the hypochlorite ions. Thus, pH value of water is generally maintained less than 7 so as to keep HOCl amount maximum. So whenever the chlorination is done in the water treatment plant, we are going to see that the pH value is maintained less than 7. That is because this HOCl will not be dissociated. If this particular HOCl amount will be maximum at this particular pH level. Disinfecting action of chlorine. Further, if we discuss, the chlorine will immediately react with ammonia present in water to form various chloramines. So, when this chlorine reacts with ammonia present in water, if at all your water contains ammonia, then this chlorine will react with ammonia in water to form various chloramines. So, what are these different chloramines in the water that is going to be formed? NH3 plus HOCl will give you NH2Cl plus H2O. NH2Cl plus HOCl will give you NHCl2 plus H2O. NHCl2 plus HOCl will give you NCl3 plus H2O. So these are the three reactions that we are going to see whenever chlorine comes in contact with ammonia that is going to be present in water. The chloramines are so formed which are stable and are found to possess the disinfecting properties. So these are the chloramines which are going to act as the disinfectant agents when the chlorine is added to the water. Are very stable and they act as the disinfecting agent in the water. They can also remove odor, that is these chloramines will remove whatever, if the water contains any pungent odor or any odor of the chlorine is present, they are going to be removed, and water, but only to a certain extent, only to a certain extent the odor is going to be removed by these chloramines. Disinfecting action of chlorine. Further, the free chlorine as well as the combined chlorine will cause germicidal action on bacteria and pathogens. So whatever the disease causing bacteria or pathogens that are going to be present in the drinking water are going to be removed by this particular free chlorine as well as the combined chlorine. So this is how the chlorination process is going to be seen in case of drinking water disinfection. The free chlorine will instantaneously kill the pathogens, while the combined chlorine will provide long-term germicidal effect. So here we are going to see the advantages of both. That is, the free chlorine which is present in the water will instantaneously kill the pathogens. The pathogens will be killed by the free chlorine, whereas this combined chlorine will be acting as a long-term germicidal effect to the water. The residual chlorine should be 0.2 mg per liter for 10 minutes contact period. So whenever this chlorination is done for a 10 minutes of contact period, we can see the residual chlorine that is present in the water should be only 0.2 mg per liter. Use of bleaching powder. So the next method after chlorination, we are going to see the use of bleaching powder. Normally this bleaching powder or chlorinated lime, what we are going to call, or calcium oxychloride CaOCl2, is also used as one of the disinfectant. It is a white amorphous powder with a pungent smell of chlorine. We can have the odor of this bleaching powder. It is very pungent in nature, pungent in smell. When fresh, it contains 30% of available chlorine. Whenever this bleaching powder is fresh, we see that 30% of the chlorine will be present in that. So this is also going to be used as one of the disinfectant for killing the germs and pathogens of the drinking water. So this is how we are going to see the disinfection process that is going to be carried out for our drinking water supply. So before going for the next part, that is a distribution system. So we are going to see some videos regarding this disinfection. We shall see one by one. That is, the first video we are going to see is how does this drinking water treatment plant work. So you can see a video showing the drinking water treatment plant working. Just I'll directly connect with the LCD. Pause the video just a minute.
Before cascade aeration, pre-chlorination is used for initial disinfection at starting point. In cascade aerator, water is allowed to flow downward through a series of steps to aerate the inlet water for imparting freshness, removal of odor, dissolved gases, iron and manganese. After cascade aerator, water flows to flash mixture cum flocculator, where coagulant chemical like alum, lime, polyelectrolyte, etc. are dosed and mixed properly by rapid mixer and passed to flocculator, where flocks are generated with the help of slow mixing by pedal agitator. This unit is used for removal of turbidity and to convert fine solid particles to bigger size flock particles. After flocculator, water is sent to clarifier, where due to gravity Incoming flocks are settled down at bottom of clarifier and clear water is sent to rapid gravity filter for filtration of remaining fine solid particles. This unit comprises a bed of sand supported on gravel overlaying an under drainage system. It is used for removal of less than 20 NTU turbidity. After filtration, turbidity is reduced to less than 1 NTU. Now, if hardness is not an issue, then water is sent to ozonation unit for disinfection. Alternatively, instead of ozone disinfection, post-chlorination can also be used for low-budget projects. After disinfection, drinkable water is ready for use and send cities drinking water overhead tank. And the sludge produced from bottom of the clarifier is sent to thickener, followed by sludge drying bed through sludge transfer pumps. Sludge drying beds comprises under drainage system. Thus, drainage liquid is further sent to clarifier and dried sludge from sludge drying beds is disposed of as per client's requirement. The method of treatment to be employed depend on the nature of raw water constituent and desired standard of water quality. Aeration, flocculation, clarification, filtration, disinfection, softening, refrigeration, defluidization, and water conditioning are various unit operations used in drinking water treatment plant. But the combination of these unit operations is completely dependent on the raw water quality and desired drinking water quality. Shown process flow animation was typical process flow diagram of drinking water treatment plant, where at inlet we expect turbidity, TSS, minimum bacterial level, dissolved carbon dioxide, and maybe odorous water. The choice of any particular sequence of treatment unit will depend not only on the quality of raw water available and treated water desired, but also on the comparative economics of alternative treatment steps applicable. Thus, if we know the inlet water quality, then we can also optimize our process flow diagram according to inlet water impurities. This optimization of unit processes may decrease the operational as well as capital cost with low maintenance and less space requirement. Thus, this is our first case where groundwater and surface water with storage which are well protected. Here, the water has turbidity below 10 NTU and they are free from odor and color. Then we can implement only plain disinfection by chlorination before supply, as shown in scheme 1 and 2. In other case, where groundwater contain only dissolved carbon dioxide and odorous gases, then aeration by either cascade aerator or any other aeration device followed by disinfection for removal of microbial contamination is sufficient for getting drinking water. Now comes to the next case. Sometimes unconventional flow sheets may be adopted for water of low turbidity, below 10 to 15 NTU and containing low concentration of suspended matter less than 50 ppm. Thus, for this scheme, inlet water flows to stilling chamber cum flash mixture cum flocculation unit with rapid and slow mixing device, where fine suspended solid particles will convert in bigger size flocks and these flocks will be separated in rapid gravity filter. Then the clear water free from TSS will be collected from launder of filtration unit and flows to treated water tank through disinfection unit. Thus, this water will be safe for drinking as it is now TSS, turbidity and bacterial infection free. Remember here, after flocculator, we have applied rapid gravity filter instead of clarifier because the inlet surface water is of low turbidity and low TSS. Where groundwater contains excessive iron, dissolved carbon dioxide and odorous gases, then process flow scheme will be aeration by either cascade aerator or any other aeration device for removal of odor and dissolved gases, followed by flash mixture cum flocculation unit with rapid and slow mixing device followed by clarifier for removal of turbidity and total suspended particles, followed by rapid gravity or pressure send filter for removal of remaining fine solid particles, followed by disinfection for removal of microbial contamination and for protecting us from bacterial infections. These are the references of this video.
So, coming for the next video, we are going to see the two simple ways which we are going to use for treating up of the water.
Every 20 seconds, a child dies because of water-related diseases, such as cholera and typhoid. The majority of diseases are due to fecal matter within the water, and transmission occurs by drinking contaminated water. You can make water cleaner and ready to drink by using this simple two-step process at home. The first step is cloth filtration. Take a large cloth, which you'll need to fold at least 4 times so there are multiple layers of fabric. Once folded, it needs to cover the opening of a storage vessel easily. Fasten the cloth, securing it around the rim of the opening and tighten with a string. Filter all water immediately at the place where you're collecting it. Gather the water, let it settle, then pour off the clear water on top. Once you've filtered the water, seal the container securely and keep it separate from the unfiltered water. If you're going to reuse the cloth, always make sure the same side is up each time. Rinse the filter cloth after each use and wash with soap if available. Make sure your final rinse uses cloth filtered water. This cloth method can be used on its own, but it's better if it's used in combination with the power of the sun. Step 2. Take a plastic bottle, like a soft drink bottle. Remove its label. The bottle must be clean, unbroken, transparent, colorless, or with a bluish tint, and it must be smaller than 3 liters. Pour the water you've collected into it, but only fill it 2/3 of the way. Tighten the cap and shake for about 20 seconds. Fill it to the top and put it on the roof of your house. Fully expose the bottle to sunlight from morning to evening for at least 6 hours. The sun will destroy the germs that cause disease. If the sky is cloudy, the bottle needs to remain in the sun for 2 days in a row. The water is now ready to drink, but you need to keep the water in the same bottle you used. Here's to your health.
So, one more video regarding the next video we are going to see. Just a minute. Advanced water treatment. So after these two simple ways, we are going to see the advanced method, that is, so one more thing before going for the advanced method, we are going to see one important terminology regarding the chlorination of this water. So here one term that comes is the breakpoint chlorination. So what do you mean by this particular breakpoint chlorination? We are going to see this video.
It's important for treatment plant operators to have a good understanding of breakpoint chlorination and other reactions that occur when chlorine is added to water for disinfection purposes. To understand how chlorine reacts when added to natural water sources for the purpose of disinfection, we should first consider how chlorine reacts in pure water. When pure chlorine is added to pure water, it reacts to form hypochlorous acid and hydrochloric acid. Hypochlorous acid is one of the 2 forms of chlorine in a free chlorine residual. When the hypochlorous acid dissociates in water, it forms the other form of free chlorine, which is called the hypochlorite ion. This reaction goes both ways and is pH dependent. As pH is lowered, the equilibrium shifts, favoring the formation of hypochlorous acid, which, by the way, is about 100 times more effective as a disinfectant than the hypochlorite ion. Now, conversely, as pH increases, the equilibrium shifts the other way, favoring the formation of the hypochlorite ion. Since there are no impurities in pure water for chlorine to react with, we expect our measured chlorine residual to equal the amount of chlorine added. For example, if we add chlorine at a dose of 2 milligrams per liter, we would expect a 2 milligram per liter residual, which is in fact what we find. And this also holds true if we increase the chlorine added to 4 milligrams per liter. And I'm sure you're not surprised to find out that if we increase the dose to 6 milligrams per liter, our pure water residual is also 6 milligrams per liter. So there's a linear relationship or a direct relationship between the amount of chlorine added and the residual that remains in solution. And this residual is a free chlorine residual that's made up of hypochlorous acid and the hypochlorite ion, depending upon the pH.
So this is what I explained before.
So depending upon the pH, there'll either be more hypochlorous acid or more hypochlorite. Well, that's a great theory, but what happens when we add this same chlorine to groundwater or surface water that has these impurities in them, such as iron, manganese, nitrite, or even ammonia, that's the result of decaying natural organic matter that's in the surface water source? Well, let's take a look and see. As we begin to add our chlorine, like we saw earlier on our breakpoint chlorination curve, between points 1 and 2, we have iron and manganese, nitrite, sulfides, and other reducing compounds, so we have no residual. Once that demand has been met and we continue adding chlorine, it's going to react with the natural organic matter and the ammonia in the water between points 2 and 3 and form that combined chlorine, which is for the most part monochloramine. And that's formed between points 2 and 3 on our breakpoint curve. Also, between points 2 and 3, this is where trihalomethanes are formed due to the reaction between chlorine and the natural organic matter in the water. And at this peak, we have a chlorine to ammonia-nitrogen ratio of 5 to 1. As we continue adding chlorine, there's a reaction between the chlorine and the ammonia and nitrogen, and it starts destroying that residual till it bottoms out at point 4, which is what we call breakpoint. At the breakpoint, we've reduced the chlorine residual as far as it's going to go, and now as we continue to add chlorine, we're going to see a linear response or a linear increase in the chlorine residual. And it'll be in the form of free chlorine. However, there remains combined chlorine with the free chlorine residual. And as we said earlier, 85 to 90% of the total chlorine residual will be in the form of free chlorine beyond breakpoint. Now, the form of that chlorine will either be hypochlorous acid or hypochlorite, and that's a pH-dependent reaction.
So this is what we are going to see, the breakpoint. So this is the breakpoint. Chlorine is nothing but it will, when you add excess amount of chlorine, we see that the free residual chlorine will be present and the required amount of chlorine will be excess in water. So next, going for the next video, that is the last, I think. It is regarding the disinfection with the ozone. So here we are having one more video. Just have a look.
Disinfecting water with ozone. With proper treatment, drinking water can taste good, even when drawn from rivers and urban areas. One treatment is advanced oxidation using high-concentration ozone. Widely used in Japan, it's now being introduced in other countries too. Ozone is an important topic in discussions about global warming. Known by the symbol O3, ozone is formed when an extra oxygen atom binds to an oxygen molecule. When ozone is dissolved in water, its oxidizing properties disinfect the water, eliminating unpleasant tastes and odors. as ozone is made from oxygen. After use, it reverts to pure oxygen and vanishes without a trace. Mitsubishi Electric's advanced ozone generation systems make river water drinkable and tasty. Ozone is generated by the silent electrical discharge method. This creates ozone by bombarding oxygen molecules with electrons. In conventional systems, some of the ozone created is broken down by electron bombardment. Research at Mitsubishi Electric has led to a reduction of the discharge gap, which minimizes the breakdown of ozone within the generator. Our ozone generators produce high concentration ozone at low operating costs. Water treated with ozone is delicious right from the tap. This is a benefit that everyone can live with.
So with this, I think everyone came to know how the chlorination process and ozone process is going to be taken place in case of disinfection of drinking water. So tomorrow we shall see the next part, that is a distribution system of this drinking water. So with this, I hope all of you have understood what is disinfection and what are the different methods of disinfection and how the process is going to be done through the PPTs as well as your videos. Okay, thank you.